So, we're looking at how to calculate work on horizontal plane part 2. In the previous video, we discovered that to apply the formula that says W is equal to F delta X cos theta, we need to establish two things first and foremost. First, we need to identify the forces that are working on the object of interest. That's why it is important to draw a free body diagram. Even if the question does not require us to draw one, it is important to draw a free body diagram because it makes the solution to the problem much easier. Then the second thing we needed to establish quickly was the direction of motion. The theta in the formula represents the angle at which we measure all the forces relative to the direction of motion. So if the object was moving east, we made the direction of motion east, and the 0 degree direction was also east. In this example, we're going to look at a situation where the object moves west, and therefore the 0 degree direction will be the west. Okay, a child pulls a box of mass 25 kilograms along a horizontal surface for 20 meters. The child applies a force of 55 newtons at an angle of 25 degrees to the horizontal. Friction is present. Okay, so this child pulls this box along for 20 meters by applying the force in 2D. Remember now, when the force is acting in 2 dimensions, it is always good to draw the components of the force so that you can see the effects of these forces in the 2 directions. We want to calculate the work done on the box by the child after moving through a distance of 20 meters west from rest, correct to 2 decimal places. So, we bring in our free body diagram. We can clearly see that the weight usually vertically downwards, the normal force vertically upwards, frictional force is always in the opposite direction of motion, and then we have our 2 important components, the Fx and the Fy. It's always important to note that when an object moves horizontally, it is the horizontal forces that are at play. So once you've drawn a component diagram like this, we can now ignore the vertical forces as far as the motion of the object is concerned. It is Fx and Fk that are responsible. Okay, so let's apply the work formula. So the object moves like that. So we're now applying the formula that says W is equal to F delta X cos of theta. Okay. 55 times cos 20 gives you 996.94 joules. So the applied force is acting at an angle of 25 degrees to the direction of motion. So in this case, the west is actually the 0 degree direction. Important to note that. Then 1.2 says the total work done on the box is 296.94 joules. Calculate the magnitude of the frictional force, correct to 2 decimal places. So the total work, we know that is given by the work done by all the forces on the object. Applied force, normal force, gravitational force, frictional force. But we've already discovered that on a horizontal surface, the work done by the gravitational force and the normal force is 0 joules. Okay, so the normal force does 0 work, weight does 0 work. So which means I'm left with the applied force and the frictional force. 296.94 is the total work that is done. It's now equal to 996.94 plus 0 work from the normal, 0 work from the gravitational force, plus the frictional force. So we can work out the work done by friction. Okay, we get the work done by friction is negative 700 joules of energy. Once we get the work done, we can always get the force. Okay, so it's one of the skills again that is important. Once you discover the work or you determine the work done, now use the work formula W equals F delta X cos theta to work out what the frictional force is. Okay, and we end up with a frictional force of 35 newtons. Alright guys, that is how you can apply the work formula when you have got a force that acts in 2D on an object. Okay, my 5 minutes is up. It's time for you guys to do some practice work. Don't disappear yet. Let's develop a skill. So, in this question, we've got a box of mass 50 kg that is pushed through a distance of 45 meters west by a force F. The force F is applied at 30 degrees to the horizontal, as seen in the diagram. The box moves at constant velocity west. So guys, in mechanics, this is a very important word, constant velocity. It's a clue to solving this whole puzzle. The moment you see the word constant velocity, it should ring a bell. If you go back to Newton's second law of motion, what happens when the velocity is constant? It's a clue. 1.1, draw a free body diagram to show all the forces acting on the box. Give a brief explanation why the normal force does zero work on the box. That's 1.2. 1.3, the total work done by frictional force is negative 4,500 joules. 1.3.1, calculate the work done by force F. 1.3.2, calculate the magnitude of the force F. So at this point you need to pause the video, and when you're ready you press play and we can discuss the various options, see if your answers agree with mine. Maybe you might want to add a comment if you really think your answers are correct, and we can discuss. So 1.1, we are asked to draw a free body diagram. To draw a free body diagram, we need to replace the box with a dot, and let's place all the forces that are acting. Remember, the simplest approach is to try and draw the forces that act in the horizontal, show the forces that act in the vertical, and that way it's easier to see what's happening. So we've got Fg, weight going vertically down. We've got the frictional force always in the opposite direction of motion. Since the box moves at constant velocity, the force that is balancing the friction must also be equal. So we know in this case it's going to be the component of that force, Fx. The other component of Fx goes vertically downwards, that is the y component, and then the normal force always goes vertically up. Okay, once I draw my T diagram like this, I can now easily see what's happening. Remember, we said the vertical forces, they tend to do zero work. Then it's these horizontal forces that will have an impact in terms of the work that is actually being done on the body. Okay. 1.2, give a brief explanation why the normal force does zero work. Guys, remember we said the direction of motion, make it the 0 degree direction. Measure the direction anti-clockwise. It means the weight is at 90 degrees. The frictional force always at 180 degrees. The normal force is at 270 degrees. If we use the work formula, okay, W, work done by the normal, is Fn, normal force, times delta x times the cos of 270 degrees. What is the cos of 270 degrees, guys? Cos of 270 degrees is 0. Okay, so this whole expression becomes what? 0. So our explanation is to say that the normal force acts at an angle of 270 degrees to the direction of motion and has got a 0 component in the direction of motion, therefore will do 0 work. Okay, normal force acts at 270 degrees to the direction of motion, will have no component in the horizontal direction and therefore will do 0 work. The same is true with these other two forces, Fy and Fg. Should be able to explain this fairly easily. Okay, it's a very important idea. We are on a horizontal surface, and all the forces that are acting vertically will have no effect in the horizontal direction. All right, let's move on to 1.3. Just allow me to create some space. I'm running out of a bit of room on my board. Okay, 1.3. Calculate the work done by force F. The work done by frictional force is negative 4500 joules. Now we need to use that idea of constant velocity. Constant velocity means now we're moving on a horizontal surface, so the forces that are going to be responsible for motion are the horizontal forces, Fx and Fk. One of those forces is going in the positive direction. One of them is going in the negative direction. Okay. So which means if the object is moving at a constant velocity, these two forces are balanced according to Newton's first law. Okay, if there is no resultant force, the object moves at velocity in a straight line. Okay, so what then does this mean in terms of work now? Okay, so if an object is moving at constant velocity, it means its kinetic energy is not changing. So if the kinetic energy is not changing, then the object is not gaining any energy. Therefore, we can now say, oh, the net work that is done on this object must be what? 0. So guys, it's important to note that whenever an object moves at constant velocity, the energy of the object is not changing. The kinetic energy component is remaining constant. Therefore, the net work that is being done is 0. Okay? The positive work being done is equal to the negative work that is being done. Okay? I think of it this way also. If the net work done was negative, what would happen to this object? Okay? Suppose W net, so let's leave this statement out. Suppose W net was negative. Then this object will be slowing down, isn't it? Okay, the object will be slowing down. So we're looking at a case when an object is moving and then it starts stopping, slowing down. The network is negative. Okay, the forces going in the negative direction begin to retard the object, and the object begins to lose energy. That's what we say negative work is all about. If the network is positive, then the object will be accelerating. So it's increasing speed, it's gaining kinetic energy. Okay. If the network is 0, then in this case, the object moves at a constant velocity. So as we go with our mechanics, we need to be aware of these ideas. Okay. Now, having said that, this puts us in a prime position now to use the idea of the net work done. The net work done is the work done by all the forces on the object. Okay. What are the forces that are acting? So we know that W net is going to be the work done by applied force, work done by frictional force. I don't need to add the other forces because I know they're going to do 0 work. The normal force does 0 work, the gravitational force does 0 work, the component Fy does 0 work. Okay. Alright, so the network we're saying is 0. The work done by the applied force we don't know, but we know that the work done by frictional force is a negative 4,500 joules. So this simply means the work done by the applied force must also be 4,500 joules. That is why the object is moving at a constant velocity. Negative work, the magnitude of the negative work is equal to the magnitude of the positive work. So the net work done is 0. Then last but not least, 1.3.2, we need to work out the magnitude of force F. Okay, so now we know the work done, we can now calculate the force. We've seen in previous video, once we know the work done, we can now calculate the force easily. We now say the work is equal to F delta X times the cos of theta. The 4,500 is equal to F times 45 times the cos of 30 degrees. Right? So we're just simply dividing both sides by 45 times cos 30. 45 times the cos of 30 degrees. Right? So, what's 4,500 divided by 45 times cos 30? You get 115,47 newtons is equal to F. Okay guys, that's how you can apply this idea of work done on a horizontal plane. Now remember, the net work done is 0 if the object moves at constant velocity. If the object accelerates, the net work done is positive. If the object slows down, the net work done is negative. Thanks for watching guys. In the next section on mechanics, on work, we will look at an interesting scenario. What happens now when the object moves on an inclined plane? Does the gravitational force continue to do nothing, do zero work, or things change? Okay, see you guys next time when we discuss these ideas. Thanks for watching. Don't forget to hit the subscribe button and like this video. See you around next time.